diffraction. Consider that you are sitting at this point in this room, and a music system kept in another room is playing music. Since the door of this room is open, you are able to hear the music even if you are not present in front of the door. This means that sound waves somehow bent across the door and reached your ears. This phenomenon of bending of wave around the corners of an obstacle or aperture is called diffraction of a wave. The process of diffraction can be explained using Huygens principle. When the waves from the music player reach the opening, according to Huygens principle, every point on the wavefront will act as source of secondary wavelength. Then the wavelength, then the bending will be almost unnoticeable. But if the opening is smaller than or almost equal to the wavelength of the wave, then the bending will be high. Now consider another situation where we have a light source instead of a music system. As we can see here, the light waves have illuminated only this part of the room. This means that the light waves did not bend to illuminate this region. This type of regions where a particular wave is unable to penetrate is called shadow region. Now the question is, why did the light waves bend so least and sound waves bend so high? The answer to this lies in the property of wave, which states that the extent of bending of any wave depends upon the value of its wavelength lambda compared to the size of the opening d. The bending of a wave or diffraction will be high only if the size of the opening d is either comparable to lambda or is smaller than lambda. Since the audible sound waves have large wavelength in the order of 1 centimeter to 10 meter, the sound waves undergo high diffraction. However, the wavelengths of visible light is extremely small compared to the size of the opening d. Due to this, the diffraction is almost negligible. Now, if we reduce the size of the opening to few micrometers, which is almost comparable to wavelength of the light waves, then the light waves undergo diffraction like sound waves. Fraunhofer's diffraction at a single slit. When a monochromatic light wave is allowed to fall on a tiny opening with size in few micrometers, the light undergoes diffraction. Now, if we place a screen in front of the opening, alternate dark and bright pattern is formed on the screen. Now let us discuss about the diffraction pattern formed by a monochromatic light source. Consider a plane wavefront XY of wavelength lambda incident on a narrow slit AB of width small a. According to Huygens principle, every point on the wavefront at the slit will become source of secondary wavelets. Waves of same amplitude are emitted from these points in all directions. With the help of a convex lens L, all these waves are focused onto a screen placed at a distance d from the slit. A diffraction pattern is obtained on the screen, and the pattern consists of alternate bright and dark bands of decreasing intensity on either side of the central maximum. Now, let's calculate what causes these bands. Now consider a point O on the screen which lies on the perpendicular bisector of the slit. The wavelets that fall on the lens L1 parallel to CO converge on point O, since the waves from these points travel equal distances to reach point O. The phase difference between them will be zero. The waves superpose with each other and produce maximum intensity at O. This point O becomes the location of central bright fringe. Now consider an arbitrary point P on the screen. all the secondary waves from the slit AB make an angle theta with CO and reach the point P. The intensity at point P depends on the path difference between the waves. Now let us draw a perpendicular AN from the point A to this ray diffracted from B. Now the distance BN gives the path difference between the secondary waves from A and B reaching point P. From triangle ANB, BN by AB is equal to sin theta and BN is equal to AB sin theta. Since AB is the slit width which is equal to A and BN is the path difference, therefore the path difference is equal to A sin theta. Now case 1. If the path difference between the waves is equal to lambda. To analyze this condition, let us divide the whole wavefront AB into two equal halves AC and CB. Since the path difference between the secondary waves from A and B is lambda, the path difference between the secondary waves from A and C reaching P will be lambda by 2. Due to path difference of lambda by 2, these two waves will interfere destructively at point P. Overall, point P will be of minimum intensity and it is called first secondary minimum, and it is formed on either side of the central maximum. The angle of diffraction theta, for which the first secondary minimum is produced, is given by the relation A sin theta is equal to lambda, or sin theta is equal to lambda divided by A. Since theta is very small, sin theta is approximately taken as theta. Therefore, theta is equal to lambda by A. If the path difference between secondary waves from A and B is equal to 2 lambda, in this case, the wavefront AB can be divided into 4 equal parts. Now, every point in a part will have a point in its adjacent part, for which the path difference is 2 lambda by 4 or lambda by 2. Hence, all these waves will interfere destructively. In general, the angle of diffraction theta n for nth secondary minimum is given by A sin theta n is equal to n lambda, where n is equal to 1, 2, 3, 4 and so on. Now let us find the positions of secondary maxima. If the path difference between the secondary waves A and B is equal to 3 lambda by 2, in this case, the wavefront AB can be divided into 3 equal parts. The path difference between the corresponding points of the first two parts will be equal to lambda by 2. Therefore, they will interfere destructively. However, the wavelets from the third unused part will interfere constructively at point P to produce a weak first secondary maxima. Similarly, second secondary maxima will be formed on the screen where the path difference is equal to 5 lambda by 2. In general, the angle of diffraction for which the secondary maximum are produced is given by A sin theta n is equal to 2n plus 1 lambda by 2, where n is equal to 1, 2, 3, 4, so on. Now, let us look at the width of the central maximum. The linear width of the central maximum is the distance between the first secondary minimum on either sides of the central maximum at O. Linear width of central maximum is given by W is equal to 2 lambda D divided by A. Here D is the distance of the screen from the slit, A is the width of the narrow slit, and lambda is the wavelength of the light. Angular width of the central maximum is given by omega is equal to 2 lambda divided by A, and the units of angular width is radian. figure here shows the intensity of diffraction pattern for single slit for various angular positions sin theta. The pattern has central bright maximum formed at point O. The angular positions of various secondary minima are sin theta is equal to plus lambda by A minus lambda by A plus 2 lambda by A minus 2 lambda by A and so on. Similarly, the angular positions of various secondary maxima are sin theta is equal to 3 lambda by 2A minus 3 lambda by 2A plus 5 lambda by 2A minus 5 lambda by 2A and so on. The intensity of central maximum is highest and the intensities of secondary maxima goes on decreasing as the distance from